Welcome to the deep dive. Today we're jumping into something really core to, well, truly smart AI systems, vision language models, or VLMs.
Yeah.
Specifically, we're going to unpack the really interesting technical stuff behind the new GLM-4.1V thinking and GLM-4.5V models. These come from the GLM-V team at Zhipu AI and Tsinghua University.
A powerhouse team for sure.
Right. And our mission today is pretty straightforward. We want to give you a really clear picture of the technical breakthroughs, the complex training they used, and how these things actually perform on all sorts of reasoning tasks.
Think of it as getting under the hood.
Exactly. What makes them tick, what makes them so powerful, and what this might mean for AI going forward. And just a reminder, we're keeping our focus squarely on the tech details and implications today. We won't be diving into the broader ethical or social discussion.
Right, sticking to the engineering and the science behind it.
Okay, let's get started.
It's definitely an exciting area because, the demand for AI that doesn't just see or hear, but can actually think and reason across different kinds of information is just exploding.
Yeah, I see that.
We're moving way past just, recognizing what's in a picture.
Mm-hmm.
The real need now is for advanced reasoning. Things solving complex science problems where you have diagrams and text together, or building agents that can, figure out how to use software just by looking at the screen. That needs a much deeper understanding than just tagging objects.
That's a really key difference, isn't it? AI has gotten amazing at one thing at a time, fantastic image stuff, incredible text generation.
Right.
But the real world, like you said, it's messy, it's multimodal, it's understanding pictures mixed with words, maybe even sounds or actions. So what exactly are these GLM-V models? Why are VLMs the next big thing?
Well, these specific models, GLM-4.1V Thinking and GLM-4.5V, they're positioned as a new family, really designed for general-purpose multimodal understanding and reasoning. And they're not small.
Oh, what kind of scale are we talking?
GLM-4.1V Thinking has 9 billion parameters.
Yeah.
But GLM-4.5V, that's a massive 106 billion total parameters.
Wow, 106 billion.
Yeah, but it uses a clever setup called Mixture of Experts, or MOE. So it only actually activates about 12 billion parameters for any given input. Makes it surprisingly efficient for its size.
That MOE approach is becoming popular, and it's really important they're open sourcing these, right? That's a big deal for the research community.
Huge contribution. Means others can build on it, test it, improve it, accelerates the whole field.
Okay, let's unpack this then. How do these models actually see and think using different data types? What's the machinery inside doing?
Okay, so at the core, both models share a basic structure. 3 main parts. First, you've got the vision encoder. This is basically the model's eyes.
Right.
It processes images, videos, turns those pixels into something the system can work with. They used AIMV2 Huge as the starting point here, which is already a very capable vision model.
Okay, so it takes in the visual stuff. And I saw something specific about video. They use 3D convolutions instead of 2D. In the vision transformer, the VIT, what's that about? Why change that?
Yeah, that's a really neat trick for video. Using 3D convolutions lets them do what's called temporal downsampling. They compress the video data by half, essentially.
Okay.
This makes processing video frames way more efficient because the model starts learning about motion and time right there in the vision encoding step. It's not just seeing static picture after static picture.
So it's not treating video like a flip book, it actually understands the flow.
Exactly. And for single images, it just kind of duplicates the image data to fit that 3D structure.
Yeah.
So it handles both photos and videos smoothly with the same pathway.
Clever. So it gets an inbuilt sense of time for videos.
Mm.
Smart. What's the next piece after the vision encoder?
Next up is the MLP adapter. Think of this as like a translator, a bridge. It takes the complex visual features from the encoder and aligns them, translates them in the same space as the text tokens. It turns the visual language into something the language model can easily understand and blend with text. Super important for mixing vision and language effectively.
The bridge. And then the final piece, the brain, maybe. The large language model, LLM, which acts as the decoder. This is where the real thinking happens.
That's exactly right. The LLM takes these combined multimodal tokens, now a mix of visual info and text, and processes them to generate the response, the reasoning, the answer.
And they use different LLMs for the 2 models.
Yeah, GLM-49B0444 for the 9B model and GLM-4.5 Air for the big 106B one. These are powerful LLMs already, but the magic is how they're adapted to really use those visual inputs during reasoning.
Speaking of adapting, images come in all shapes and sizes, right? Wide panoramas, tall infographics, that's always a headache for VLMs. How do they handle that without squishing the image or making it super complicated?
All right, that's a classic problem. They have some really smart enhancements in their vision encoding for this. Two main things. First, they integrate 2D rotary position embeddings, or 2D ROP, into the ViT's attention layers.
ROPE is usually for text sequence position, right?
How does it work in 2D for images?
Yeah, it's innovative. Basically, it lets the model understand where image patches are relative to each other. Even if the image has a crazy aspect ratio, like over 200:1, or if it's super high res, like 4K or more, it does this without distorting that spatial understanding.
So it knows where things are in the picture, no matter if it's stretched really wide or tall. That sounds incredibly useful for real-world images.
Huge practical advantage. And the second part builds on that. They keep the original absolute position embeddings that the VIT was trained with.
Okay.
But during training, they dynamically adapt these using something called bicubic interpolation. For any input image, they figure out the normalized coordinates for each patch, and then use those coordinates to sample from the original embedding table. It's like having a dynamic scaling tool for positional info. That sounds elegant. So they keep the valuable pre-trained knowledge, but can still handle different input sizes flexibly. Very robust.
Exactly, and they didn't stop there. To boost spatial understanding on the language side, they extended ROPE to 3D ROPE within the LLM itself.
Wait, 3D ROPE in the language model, what does that mean?
It means the LLM isn't just processing abstract text and image tokens, it's also got a richer, built-in understanding of the spatial layout from the visual input. It directly connects the visual arrangement to the language processing. It's subtle, but powerful for grounding language and vision while keeping the text ability strong.
Whoa. So the language model intrinsically knows about the 3D space of the visuals it's seeing. That feels like a big step towards more, human-like reasoning. And for video, after handling space, they have this thing with time index tokens.
Yes, this is quite clever for handling time in videos properly. Videos aren't just a sequence of images, they have real timestamps. So after each token representing a video frame, they insert another token, a time index token, that literally encodes the timestamp of that frame as text, like 0.5 seconds.
So it's not just frame 1, frame 2, it's frame at 0, it's frame at 0.5, it's frame at 1.2. It gets a concrete sense of elapsed time.
Exactly. It explicitly tells the model the real-world time gaps. This massively boosts its understanding of temporal relationships, which is absolutely crucial for analyzing complex video content.
It's amazing how they've tackled these really fundamental issues, aspect ratios, time so systematically. It makes you wonder, though, what new challenges pop up when a model has to grasp both the spatial layout inside an image and the time dynamics across video frames all at once. Could those things conflict somehow?
That's a really deep question. You're right, it's synthesized in two very different dimensions. Imagine tracking an object moving that's temporal while also understanding its position relative to static things in the background that's spatial. The internal math for that could get incredibly complex, maybe lead to higher processing costs, or even new kinds of errors if the spatial and temporal cues don't quite line up in the model's interpretation. The paper doesn't call this out as a limitation, but you can see their architecture is designed precisely to handle this complexity.
Makes sense.
Yeah.
It's pushing how models blend different info streams. Okay, so moving from architecture, let's talk about how they actually train these things. Their philosophy seems very focused on reasoning.
Absolutely. It's not just building a VLM, it's building one that reasons well. They lay out a 3-stage pipeline, pre-training, then supervised fine-tuning, SFT, and finally scalable reinforcement learning, RL. And yeah, they stress these are all connected, all aimed at boosting reasoning.
Okay, phase 1, pre-training. Building the foundation. They mentioned the power of diverse data here.
Yes, the foundation is everything. And it starts with a massive diverse data set. You need broad data to get strong basic capabilities across many different areas.
And this is where it gets really interesting. The sheer scale and how they curated the data. It's not just dumping data in, it's cleaning, structuring. They started with over 10 billion image text pairs, from LAION, data comp, etc. But they didn't just use it raw, right? Tell us about the curation.
Right, that raw web data is noisy. They did a multi-stage refinement, filtering out low-res images, solid color images, bad captions, duplicates. Then they used CLP score, basically a measure of image text relevance, to keep only pairs where the text actually matched the image reasonably well. Score 0.3.
Okay, so cleaning it up.
And they did concept-balanced resampling. Web data has tons of pictures of common things, very few of rare things, though. They try to balance that out.
And then this factual-centered recaptioning, that sounds like more than just filtering. They're actually improving the captions.
They are. It's an iterative process. They trained a model to basically rewrite the original captions, make them richer, more descriptive, but crucially, without adding stuff that wasn't true to the image.
Like the example they gave, a northern cardinal singing becomes a northern cardinal perched on a tree branch set against a clear blue sky.
Exactly. It's not just cleaning. It's actively enriching the training signal, teaching the model better vocabulary and how to describe complex scenes right from the start. A big step beyond just basic labels.
So, improving the data itself. Smart. And what about interleaved image text data from web pages, books? That stuff must be incredibly messy.
Super messy. Ads, menus, irrelevant text. For web data, they filtered hard, got rid of noise like
Yeah.
ads, QR codes, prioritized images that seem to have more information, like charts or diagrams, using a classifier they trained.
Mm-hmm.
For academic books, they processed over 100 million. They use tools like LaTeX XML to parse PDFs, especially from places like RCF, to get high-quality text interleaved with figures, particularly in STEM fields. The detail here is incredible.
Wow. And then OCR data, 220 million images just for reading text in images.
Yeah, covering all bases. Synthetic documents with different fonts and backgrounds, real-world photos with text, using tools like Paddle OCR to get bounding boxes for the text, and academic documents processed using methods inspired by NuGet to handle structured text from LaTeX sources. Really comprehensive text recognition training.
It covers so many scenarios where text appears visually.
Then there's grounding data, teaching the model where things are. They use datasets like LAON, combined with models like GLIPv2 to get bounding boxes for nouns and captions. But the really novel part is their GUI grounding dataset.
Ah, yes, the graphical user interface data. How do they build that?
They scraped screenshots from Common Crawl, used a tool called Playwright to automatically extract the structure of the web page, the DOM elements and their locations, bounding boxes. Then they generated 140 million question-answer pairs, specifically about interacting with GUIs. Things like click the button labeled Submit.
That's essential for billing agents that can use software, right? Very practical.
Absolutely. And for video data, they curated a large, high-quality set from various sources. They didn't just rely on basic captions. They got fine-grained human annotations for complex actions, text appearing in the video, even things like camera movement or shot type. Really deep video understanding, plus rigorous filtering and deduplication.
It's like they annotated the director's cut.
Sort of.
Hmm?
And finally, instruction tuning data. This is about making the model versatile, able to follow instructions. They built a detailed taxonomy of tasks, created complex scenarios like interacting with GUIs or understanding long documents, and checked carefully to avoid accidentally training on benchmark data. It all feeds into making the later RL phase more effective. The level of data engineering is just immense.
It really is. That meticulous curation must be a huge part of why these models perform so well. Like you said, that foundation sets the ceiling.
Definitely. The quality and diversity of pre-training data is arguably the biggest factor in the final potential of these huge models.
So how did they actually train on all this? What did the training recipe look like? That must have been a massive compute job.
Oh yeah, huge. They split it into two stages. First, the main multimodal pre-training. This built the general abilities. They use complex parallelism techniques, tensor parallel for the 9B model, expert in pipeline parallel for the 106B beast, basically, smart ways to split the work across tons of GPUs.
To think all those parameters busy.
Right. They use a sequence length of 8,192 tokens, a big global batch size of 1,536, ran for 120,000 steps, really pushing the hardware efficiently with techniques like data packing.
And after that initial pre-training, they did a long context continual training stage, pushing it even further.
Exactly. This was specifically to boost performance on high-res images, video, and really long sequences. They added more video data, more long interleaved documents, over 8K tokens, and cranked the sequence length up to a whopping 32,768 tokens.
32,000 tokens, that's a huge context window.
Massive. They adjusted their parallelism too, context parallel size 4. This stage ran for another 10,000 steps. This is continuous training that really gives it the ability to handle those very long inputs.
Okay, that foundation sounds incredibly solid. Now, phase 2, supervised fine-tuning, SFT. They call this the bridge to reinforcement learning, getting the model ready for long chain-of-thought reasoning. What's the goal here?
Right, SFT here isn't really about teaching new facts. It's about teaching the model how to think and respond. It aligns the model's existing knowledge with a specific reasoning style, like teaching it to show its work step by step.
So it provides a better starting point, a stronger cold start for the next phase, RL.
Exactly. It primes the model to generate coherent, structured thought processes, which makes the RL phase much more effective.
How do they get the data for this long chain of thought data? What makes it high quality?
They curated a special data set, lots of examples of multi-step reasoning. Mostly verifiable tasks like STEM problems where you know the right answer, but also some open-ended questions to keep it general. They even used the pre-trained model itself to filter the data, keeping problems that were moderately difficult, not too easy, not impossible.
Challenging it just enough. And they use that very specific standardized response format, right, with the think and answer tags.
Yes, that's crucial. Think the reasoning steps, think answer, the final
For
answer.
few performers with a definite answer, they box it. Begin off box, final answer.
Why so rigid?
It's all about making life easier for the reinforcement learning phase later. That explicit boxing makes extracting the final answer for automatic checking absolutely reliable, no ambiguity. They even added those tags as special tokens the model learns. It seems like a small detail, but it has a huge impact on how stably and effectively the RL can work. It needs a clear signal.
Makes sense. You need to know exactly what part of the output is the answer you're supposed to be grading. They also mentioned feeding good examples from RL back into SFT, like a feedback loop.
Yeah, iterative improvement. The SFT training itself is full parameter fine-tuning using that long 32,768 token context, but with a smaller batch size, 32. And importantly, they mix in high-quality text-only long reasoning examples too.
Why the text-only stuff?
To make sure the model doesn't forget how to be a good language model. You don't want its core language skills to degrade while it's learning all this multimodal reasoning.
Good point. Keep the foundation strong. And they noted that even messy reasoning data helps a bit, but clean, consistent data is way better for RL stability and performance. Quality matters, especially here.
Definitely. Connecting back to the big picture, this SFT stage, with its careful data and strict formatting, is really about setting the stage for RL. It creates a predictable environment. Without that clear structure for thoughts and answers, RL would struggle to know what to optimize. It's giving the model a clear rubric, like you said earlier.
Right, makes perfect sense. Okay, now for the grand finale. Phase 3, reinforcement learning, RL. This is where they really dial up the performance.
This is the main event for boosting reasoning. They use a mix, RL with verifiable rewards, RLVR, where they can automatically check the answer, and RL with human feedback, RLHF, for more subjective tasks. This is where the model really learns from feedback on its outputs.
And the reward system is key. Getting that right for diverse multimodal tasks must be tough. What were the big challenges?
Two main ones they highlight. First, just reliably extracting the final answer for the automatic checks, RLVR. Using another LLM to find the answer sounds flexible, but they found it breaks down on complex multimodal questions, especially if the model's answer part gets long or weird.
So the explicit begin box tags solved that.
Exactly. Made it foolproof for RLVR. The second, bigger challenge is avoiding reward hacking.
Ah, yes. The model finding loopholes to get the reward without actually getting smarter, like answering a number between 0 and 10 for a counting task.
Precisely. And they stress this. A weak checker in any one area can mess up the entire training process. Their Figure 5 shows this clearly. A bad checker for multi-image QA caused the whole model's performance to collapse, even on STEM, where the checker was fine.
Wow. So one weak link breaks the whole chain. That raises an important question. If a model can hack the reward system, doesn't that undermine the whole purpose of learning?
It absolutely does. It means you're optimizing for a flawed goal. You might get higher scores on your internal metrics, but the model isn't actually becoming more capable or reliable in the real world. That's why robust, hack-resistant reward design is so critical.
So how did they solve it? How did they build a robust reward system?
Their solution was a comprehensive, domain-specific reward system. Tailored checkers for different task types. They have some shared checks like basic format validation or exact text matching, but then specialized logic for each domain.
Can you give some examples?
Sure. For STEM, math, physics, chem, they use tools like SIMPy for precise numeric matching, allowing for some tolerance. They even use another LLM just to check if the units in physics chemistry answers are correct.
Okay.
For long documents, charts, OCR, they use LLM-based semantic matching for document questions, specific numeric text checks for charts, and edit distance for OCR accuracy.
What about visual tasks?
For visual grounding, finding objects, they use intersection over union, IOU, how much the predicted box overlaps the true box. For GUI agents, it's a mix. Checking if the predicted action is right, like click, and using IOU to check if it targeted the correct UI element, very specific to interaction.
Makes sense.
And for video, it's exact or semantic matching using an LLM. Crucially, they also have format and style checks. They penalize the model if it uses the answer box markers incorrectly, or if it mixes languages weirdly, or gets repetitive in its thinking. It's a really detailed, multifaceted reward system designed to prevent gaming.
That level of detail in the reward function is incredible. All this feeds into their main RL strategy, reinforcement learning with curriculum sampling, RLCS. What problem does that solve?
Efficiency, mainly. As the model learns during RL, lots of the training examples become too easy. The model gets them right almost every time.
Right, so it's not learning much from those anymore.
Exactly. But processing them still takes up valuable GPU time. They found in early tests that sometimes more than half the prompts were getting over 90% accuracy pretty quickly. That's a lot of wasted computation on stuff the model already knows.
So RLCS is like an AI tutor making sure the model always works on problems that are just the right level of difficulty. How does that work?
Pretty much. They grade the difficulty of examples both offline, before training starts, using other models or humans, and online, by tracking how the model is actually doing on them during training.
Okay.
Then they dynamically adjust which examples get sampled. They sample fewer of the trivially easy ones and the impossibly hard ones, and more of the ones in that sweet spot, challenging but achievable. This focuses the learning where it counts, making the whole process much faster and more effective.
Super efficient. What else did they do to make RLCS work even better?
They found a larger batch size helps, especially with diverse multi-domain data. They also introduced something called dynamic sampling expansion via ratio EMA. This tackles a problem where sometimes a whole batch of attempts might be all correct or all incorrect, which gives a poor learning signal.
Right, you need a mix.
So they actually sample more attempts than they need for the batch, and then carefully select a subset that has a good balance of correct and incorrect responses. This stabilizes the effective batch size and makes sure every training step is informative.
Clever way to guarantee useful feedback. And this force answering thing.
Yeah, that handles cases where the model's thinking process gets cut off by the maximum length limit before it actually gives an answer.
Yeah.
Normally, that would get 0 reward, even if the thinking was good. So they automatically insert the think token to force it to output something as an answer. This ensures it gets fair credit for its partial reasoning, and also teaches it to be concise and provide an answer even if its thinking time is limited. Very practical.
That prevents wasted effort and teaches conciseness. Now, this one surprised me. They discarded KL loss. Isn't that commonly used in RL to keep the model from changing too drastically?
It is common, yeah.
Yeah.
KL divergence measures how much the model's output probabilities have shifted from the original model. They found that for VLMs, this divergence tends to increase faster than for text-only models. But when they tried using KL loss to constrain it, it actually hurt performance, kind of stifled the model's learning.
So they just took it out.
Yep, found it worked better without it. They also tweaked another parameter. They increased the upper limit for important sampling ratio clipping, calling it clip higher. This helped with stability when learning from past experiences, off-policy learning, and prevented the model's outputs from becoming too narrow or predictable, entropy collapse.
Interesting trade-offs there. They also shared some cool insights from doing RL across so many different domains, like how well a model did right after SFT doesn't perfectly predict how high it can get with RL.
That's a big one. It implies that the RL phase itself can really unlock potential. Two models might start SFT at different levels, but if they have similar underlying capability, RL might bring them both up to the same peak performance. It really highlights the power of RL.
And the other big insight was about cross-domain generalization. Learning in one area helps in others, and maybe less interference than during SFT.
Yes, that was fascinating. They saw improvements in one domain, boosting performance in others. Suggests the model is learning more general reasoning skills, not just task-specific tricks. It hints that a more unified intelligence might be emerging through this process.
That's really the goal, isn't it? More general intelligence. What about keeping RL stable? It can be notoriously tricky.
They found several key things. First, SFT data quality is paramount. Bad thinking paths or formatting in the SFT data can make RL unstable or even cause it to crash. Clean SFT is crucial. Second, removing entropy loss actually helped stability for them, preventing garbled output, even though it's often used to encourage exploration.
Counterintuitive, but it worked for their setup.
Third, using top P for generating responses during training rollouts. Many people reduce top P, like 2.9, to make rollouts less random, but they found top P1 using the full vocabulary probability distribution actually prevented the model from forgetting rare words and kept the output cleaner over time, improving stability and performance.
So more randomness initially led to better stability long-term. Interesting.
Yeah. They also found calculating the loss per sample, not per token, was more stable. And a key piece of advice: make sure the model learns the output format, think, answer, etc., perfectly during SFT. Don't rely on RL to fix formatting errors. That just distracts it from learning the actual reasoning.
Get the basics right first. All these tweaks, plus infrastructure optimizations like load balancing and sequence splitting, are needed to make this kind of massive RL training feasible.
Absolutely, it's a huge engineering effort on top of the research insights.
Okay, so after all that incredibly detailed architecture design, data curation, and multi-stage training,
Yeah.
how did they actually do? What does the performance look like?
They tested them rigorously. 42 public benchmarks across 8 categories: general VQA, STEM, OCR docs, grounding, spatial reasoning, GI agents, coding, video. Really comprehensive. And they use standard tools like VLM for running the models and even GPT-4o to help score the answers fairly across comparisons.
And the headlines. How did GLM 4.5V perform?
State-of-the-art among open source models, pretty much across the board.
That's huge. Better than other open models.
Yes, and remarkably, it's competitive with, or sometimes even better than, powerful closed-source models like Google's Gemini 2.5 Flash, especially on really tough tasks like coding and controlling GUIs.
Wow. And the impact of RL was clear.
Oh yeah, they saw gains of up to plus 10.6% just from the RL phase on coding benchmarks. That's a massive improvement, really showing their RL approach paid off.
And what about the smaller one, GLM-4.1V-Thinking, the 9B parameter model? How did it fare?
Impressively well. It actually beat much larger open source models like the 72 billion parameter Quinn 2.5VL on 29 of the 42 benchmarks.
A 9B model beating a 72B model on that many tasks.
Exactly. It shows an amazing balance between performance and efficiency. For anyone needing strong VLM capabilities without needing, a national lab's worth of GPUs, that 9B model looks incredibly compelling. Premium results without the supercomputer.
That's a really important point for practical deployment. Looking at specific areas, how did they do?
Strong across the board, really. Good general visual reasoning. Top scores in STEM on hard science and engineering benchmarks, showing it can handle complex math and symbolic reasoning combined with visuals.
Like interpreting diagrams in physics problems.
Exactly. New state-of-the-art in OCR, chart and document tasks. Great at understanding long documents, too, which is vital for many real-world applications like analyzing reports.
And the GUI agents and multimodal coding, you said it excelled there.
Big time. A significant lead over competitors. This really highlights its ability to connect what it sees on a screen with the code or actions needed. Imagine it looking at a web design and generating the React code, or following instructions to book a meeting in a calendar app. That's what it's doing.
Truly agentic. And video and spatial reasoning.
Very strong spatiotemporal reasoning, understanding things happening over time and space in videos. Solid results in visual grounding, too. It really seems to handle dynamic visual content well.
Now, you mentioned this cross-domain generalization in RL earlier. They did specific experiments on this.
Yes, on the 9B model. They trained it with RL using data from only specific domains, just STEM, just OCR chart, just grounding, just GI agents, and compared that to training on a mix of everything.
To see if learning one skill helps others, what did they find?
2 key things. First, single domain training often boosted other domains. Training only on STEM problems actually made the model better at visual grounding and GUI tasks, too.
Really? STEM helping with clicking buttons.
Apparently so. And training only on GUI agent tasks improved performance across all other domains they tested.
That makes sense, maybe. GUI tasks need a mix of skills, reading text, seeing layout, planning steps.
Exactly. It seems to force the model to develop a really well-rounded set of underlying abilities that transfer. Second finding. Joint training was even better. Training on the Mixol data generally gave bigger improvements, especially in STEM, OCR chart, and general VQA, than training on any single domain alone. There's a clear synergy.
This cross-domain stuff is fascinating. It really suggests training on diverse, complex problems builds more general, robust intelligence. But it makes you wonder how exactly these different skills help each other. What are the shared mechanisms? Could we design training specifically to maximize the synergy, like a targeted workout plan for AI cognition?
That's the frontier, right? What are those underlying cognitive primitives? Maybe it's abstract pattern matching, or logical deduction, or understanding causality. If a GUI task forces better procedural understanding, maybe that directly helps solve a multi-step math problem. If we could map these shared skills, we could potentially design training curricula that are way more efficient at building general intelligence by targeting these core abilities across different modalities. Huge area for future work, understanding the how of that synergy.
Definitely. And they showcase these abilities with some really cool qualitative examples in the paper, like the UI code generation, taking a picture of a user interface and spitting out working React code.
Yeah, that's pretty mind-blowing. Turning pixels into functional software. Huge for developers.
And the video descriptions are incredibly detailed, not just man walks dog, but capturing actions, expressions, even the mood of the scene. The Chinese example shows it works cross-lingually too.
Or the video QA about capillary action. It watches the video, understands the physics concept, and explains why the water moves. That's perception, knowledge, and reasoning fused together.
The GUI agent example is wild too. Creating a calendar event by clicking specific spots using coordinates like 27,840,122,885. That's precise interaction based on instructions.
And the chart QA, pulling specific data points from a complex infographic, needing visual parsing and data interpretation.
Plus the OCR plus coding example, finding and fixing a Python bug from an image of the code. That's recognizing code, understanding logic, and correcting it, all visually grounded.
It tackles hard academic problems too. Chemistry structures, geometry diagrams, integrating the visuals with domain knowledge, and the long document summary example, handling a multi-page financial report, the spatial reasoning, figuring out where objects would be after moving, and the visual grounding, drawing accurate boxes around objects based on descriptions. These examples really make the capabilities concrete.
It's an impressive suite of abilities. But, okay, they can't be perfect. What are the acknowledged limitations? Where do they still fall short?
Right, they're upfront about this. One key issue. RL makes the model better at getting the right answer, but not necessarily better at the reasoning process itself.
How so?
A flawed or even nonsensical chain of thought might accidentally lead to the correct final answer. If that happens, RL reinforces it. So the model might be right for the wrong reasons. Getting the answer right doesn't guarantee sound logic.
That's a really tricky problem. The model could be gaming the system internally in ways we don't see just by checking the answer. What else?
RL training itself, especially at this scale, is still quite sensitive. Small changes in setup can lead to big differences in how deep the reasoning goes or the style of the output. It's still hard to get perfectly consistent results every time. It's not quite a fully industrialized process yet.
And visually, where are the weak spots?
They mention struggles with really complex visual scenes. Think very cluttered images, objects hidden behind others, occlusion, or just really ambiguous details. In these cases, the model might resort to guessing rather than being truly confident based on the visual evidence. Visual common sense is still developing.
Okay, so still room for improvement there. What about future work? Where do they see this going?
A big focus is on better reward systems. They want rewards that don't just check the final answer, but can actually evaluate the intermediate reasoning steps. Can the reward model detect if the thinking itself is flawed, or if the model is hallucinating steps? That directly tackles the right answer for the wrong reason problem.
That sounds crucial, like grading the working, not just the final number.
Exactly. They also want better ways to prevent reward hacking, especially for subjective tasks where there isn't one single right answer. And exploring multimodal transfer learning, can learning to reason about code and images actually make the model better at coding when it only sees text, finding those cross-modal synergies.
That would be powerful if seeing helps reading. And finally, benchmarks.
Yeah, evolving evaluation. Current benchmarks are getting too easy for top models, or they don't catch subtle errors like flawed reasoning. We need harder, more diagnostic benchmarks that really probe for these failure modes, shortcut thinking, hallucination, to measure true progress accurately.
This really goes back to that question. As models get better answers, how do we ensure their thinking is sound? That seems like the next massive hurdle for general AI validating the process, not just the outcome. It's about building trust and reliability into these incredibly complex systems.
Could agree more. It's moving beyond performance metrics to ensuring genuine understanding and robust reasoning. That's vital if we want to deploy these systems in high-stakes situations.
Well, this has been an absolutely fascinating deep dive into GLM-4.1V thinking and GLM-4.5V. It's undeniable that the GLM-V team has pushed the boundaries significantly here.
Absolutely. From the clever architectural choices like the 3D convolutions and Rho-P adaptations to that incredibly detailed reasoning-focused training pipeline, the massive pre-training, the structured SFT, the really sophisticated RL with curriculum learning, it's a monumental piece of work.
And the performance speaks volumes. State-of-the-art, open-source results, competitive even with closed models, and those incredible insights about cross-domain generalization. Plus, making them open source is just a massive boost for the whole field.
These models really do feel like a significant step towards truly general-purpose multimodal reasoning. They're pushing AI to perceive, understand, and reason in much more connected and complex ways.
It makes you think. Imagine an AI that doesn't just process sight and language, but genuinely reasons and adapts its thinking like we do. What new kinds of interactions, what new innovations does that unlock? It's the future these kinds of technical leaps are pointing towards.
It's definitely an exciting space to watch. We really hope this breakdown gave you a solid technical understanding of what's going on inside these impressive models. Knowing these details is key to grasping where AI is heading.
Exactly. Keep digging, keep learning. Thanks for joining us on the deep dive.